Today I'm going to teach you guys a little bit about probability trees. Probability trees are used to analyze probabilities. They can be helpful to break probability problems up, help you organize your thoughts, and let you know why you're multiplying or adding what you are. Such as an event as coin tossing, they're independent events because whether you toss the coin once, twice, 500 times, what you got the time before is not going to affect whether you get heads or tails the next time. There's a 50% chance of getting heads and a 50% chance of getting tails. Combination probabilities are probabilities where you want to find out what happens if you have more than one outcome, such as what's going to be the probability of you flipping a coin 2 times and getting a heads and a heads outcome, or a heads and a tails outcome. To find these probabilities, you multiply along the corresponding branches. So here you have your initial coin toss of getting heads or tails, which is 50% on each. And then again, if you got heads, your next toss has a 50% chance of getting heads or 50% chance of getting tails. And what you would do to find a heads and a heads is you would multiply along these lines. So you would take 0.5 times 0.5 to get a probability of 0.25. Same if you want to find any of the other ones. So a heads and a tails combination, or a tails your first time and a heads your second time. You're going to continue to multiply along these branches. In this situation, nitric oxide hypoxic respiratory failure is a serious condition that affects some newborns. If a newborn has this condition, it is often necessary to use ECMO to save the life of the child. However, ECMO is an invasive procedure that involves inserting a tube into a vein or artery near the heart, so physicians hope to avoid the need for it. One treatment for hypoxic respiratory failure is to have the newborn inhale nitric oxide. To test the effectiveness of this treatment, newborns suffering hypoxic respiratory failure were assigned at random to either be given nitric oxide or a control group. In the treatment group, 45.6% of newborns had a negative outcome, meaning that either they needed ECMO or that they died. In the control group, 63.6% of newborns had a negative outcome. So if we have the question, if a newborn is chosen at random, there's a 0.5 probability that the newborn will be in a treatment group, and if so, a probability of 0.456 of getting a negative outcome. This means that there's also a 0.5 probability that the newborn will be in the control group, and if so, a probability of 0.636 of getting a negative outcome. What would be the probability of getting a negative outcome? So it's a 50% chance whether the newborn is in the treatment or the control group. It's been stated that if they're in the treatment group, there's a 0.456% of getting a negative outcome. You may be wondering where this 0.544 number comes from. Well, in probability trees, the numbers on the tree always have to equal 1. So since 0.456 is given to us, we can subtract that from 1 to find the other half of the probability tree. They always, always, always have to equal 1. So like how we did in the heads and tails, the coin tossing event, you have to multiply along the lines. So to find the negative outcomes, you find the treatment times the negative outcome, which would be your treatment and your negative. So 0.5 times 0.456 is going to be 0.228. And the same with control along the negative outcome, which is going to be 0.318. To find the probability of getting a negative outcome whatsoever, you add those together. So the probability of getting a negative outcome here is going to be 0.228 plus 0.318, which is 546, or about 55%. Here's just another problem related with pregnancy. If a woman takes an early pregnancy test, she will either test positive, meaning that the test says she's pregnant, or negative, meaning that the test says she's not pregnant. Suppose that a woman really is pregnant, there's a 98% chance that she'll test positive. Also, if she's not pregnant, there's a 99% chance that she'll test negative. If 1,000 women take early pregnancy tests and 100 of them really are pregnant, what's the probability that a randomly chosen woman is going to test positive? Well, you're going to have your percentage of women that really are pregnant. So 0.1 is the percentage of 100 women that are pregnant out of the 1,000 women that are being tested. The 0.9 comes from, again, the tree has to equal 1. So you would take 1 minus 0.1, which would be 0.9 to the other half of the tree. it's 98% chance that a pregnant woman will test positive. So there's your that, there's your 0.98%, and then you're going to have your 0.02 from being negative, because once again, they have to equal 1. Same with if they're not pregnant, there's a 99% chance that they're going to test negative, so you have your 0.01 that they're going to test positive. So what's the probability that a randomly chosen woman from this group is going to test positive? Well, you have to have your pregnant women that are positive, so multiply along that line, which is your percentage here, and your not pregnant women that are going to test positive, which is going to be your number here. You add those together to get about 11%. So the same problem, only 1,000 women take the early pregnancy test and 50 of them really are pregnant. It's not going to change your percentages of how effective the test is, but it's going to change your original probability tree. The 0.05 is the percentage that 50 of the 1,000 women really are pregnant. So it's just going to change this first line and what your multipliers are. So the same question is how many people from this group are going to test positive. You're going to have a different number here because your original probability tree is different. You're going to have 0.05 times 0.98 for your pregnant and positive, and 0.95 times 0.01 for your negative and test positive. So from this group, about 6% of these women are going to test positive. Another way to find probabilities is by using a contingency table, and it just shows the association between two variables. You're going to have rows and columns, and it's going to show just a different way to organize your information. So suppose that a particular test has a 95% chance of detecting the disease of a person that has it. This is called sensitivity of the test, and 90% chance of correctly indicating that the disease is absent of a person that does not have it. This is called the specificity of the test. Suppose 8% of the population has the disease. What is the probability that a randomly chosen person will test positive? Well, if 8% of the population has the disease, then you're going to have 92% of the population does not have the disease. Again, the tree has to equal 1. If 95% of them that do have the disease test positive, you're going to have 5% that have the disease test negative. If 90% of the people that don't have the disease test negative, you're going to have 10% that don't have the disease test positive. These are your true positives, your false negatives, all of that. So you have your true positives are people that have the disease and test positive. Your false negatives, people that have the disease and test negative. Your false positives, people who don't have the disease and test positive. And your true negatives, people that don't have the disease and test negative. So the probability that a person that has this disease or a person that takes this test is going to test positive, it's going to be about 17% because you have your positives plus your non-positives added together. About 17%. To form that into a contingency table, you take all of your percentages and multiply them by 1,000 to get rid of the decimal. You put those into a table such as this: people that have the disease test positive, people that have the disease and test negative, people that don't have the disease and test positive, people that don't have the disease and test negative. You're going to have all of your totals here. If we have a question such as, if Mr. X is randomly selected from the population, what is the probability that Mr. X has the disease? You take your probability of your true positives over your probability of all the positives to get your percentage of about 45%. I hope this answers your questions about probability tables.